Alright, in this video I'm going to look at the notion of a basis for a vector space, and all a basis is, it just ties together the notions of linear independence along with the notion of a spanning set. So we say a collection of vectors v1, v2 up to v sub n. We say that those are a basis for the vector space if two things happen. We want the vectors to span the vector space, and we also want these vectors, the vectors in the set, to be linearly independent. And if those two things happen, we talk about having a basis of a vector space. So to me, kind of the notion of a basis is, it says you have sort of just enough vectors, to somehow write any other vector in that space as a combination of those other vectors. So somehow, to me, it's kind of like you have the fundamental tools there to rewrite anything that you want. They're kind of the basic building blocks to get the work done. Is to me, and there's just enough. If you had some extra ones, then they wouldn't be linearly independent anymore. So it says you have just enough to get the work done. They're linearly independent, and then they span the entire space. So if that makes any sense, probably not the best intuitive idea. So a couple things here. So the unit vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, these are a basis for R3, for example. I'm not going to justify that at all. If you don't believe me, I will leave that as an exercise for you, dear viewer, to think about and to justify. And hopefully shouldn't be too terribly difficult from the definitions. And if you're not sure, well, I am going to do an example here to determine if these vectors, the vector 1, 1, 1, 0, 1, 0, 1, 2, 3, are those also a basis for R3? Well, I'm going to do two things. I'm going to show that they span R3, or try to, and I'm also going to show that they're linearly independent. So the first thing I'm going to do is actually show that they're dependent or not. Excuse me, if they're linearly independent or not. So I guess we could say if they're linearly dependent or not. That's also correct, but right, if you answer one, you answer the other. So again, for our vectors to be linearly independent, when we multiply these by real number scalars, a1, a2, a3, we add them up, we set that equal to the 0 vector. It says that they'll be linearly independent if the only solution we get to this system is the trivial solution. So I'm really just trying to determine if I have trivial solutions or non-trivial solutions. So I'm going to do -1, row 1, add that to row 2 to get my new row 2, and then I'm going to do -1, row 1, add that to row 3 to get my new row 3. Alright, so we'll leave the first row alone, 1, 0, 1, 0. So -1 plus 1 is 0, we'll get 0 plus 1, we'll get -1 plus 2, which is 1, and then we'll get a 0. If we do -1 plus 1, again that's 0, we'll have 0 plus 0. Then we'll have -1 plus 3, which is 2, and then again we'll just have a 0. So the next thing I'm going to do, well, I can certainly just take 1/2 of row 3 to get my new row 3. And again, I want a 1 in the first row, first column, zeros everywhere else, I have that. I want a 1 in the second row, second column, I have that. And I want zeros everywhere else, so hey, this problem's obviously set up a little conveniently because that immediately happened. And then I want a 1 in the third row, third column, so I'm just going to divide by 2. So I'm going to, instead of rewriting this all one more time, hey, if we divide everything by 2, the only thing that's going to happen is the 2 will turn into a 1. And now we can just do -1, row 3, add that to row 1 to get our new row 1. And -1 times row 3, add that to row 2 to get our new row 2. And again, in the sake of being brief here, the only thing that's going to happen is if we take -1 times row 3 and add it to row 1, we'll get -1 plus 1, which will make that into a 0. If we do -1 times row 3 and add it to row 2, it'll make that 1 also into a 0. And this now tells us that our solution would only be if our constants, a1, a2, a3, are all equal to 0. So it says a1 would have to equal 0, a2 would have to equal 0, and a3 would also have to equal 0. which tells us we only have the trivial solution. And since we only have the trivial solution, that means yes, they are linearly independent. Okay, so they are linearly independent, so one thing's down. Now let's check if they span all of R3. Okay, so do they span all of R3? And again, what we're looking for, we want to be able to take linear combinations. So A1 times 1, 1, 1 plus A2 times the vector 0, 1, 0 and A3 times the vector 1, 2, 3. And what we want to be able to do, if we can use these vectors to span all of R3, it says we should be able to figure out constants so that we get any old vector x, y, and z that we want. Okay, so we have to justify that we can do this. So I'm going to write it as just a linear system. So we would have 1a1 plus, well, 0a2 plus 1a3 equals x. And again, I've got some examples about this when we talk about in the video with spanning sets. So this is just really a little bit redundant, just tying those two concepts together, independence and spanning sets. So our next equation would be 1a1 plus 1a2 plus 2a sub 3. We can set that equal to y. And then we would have 1a1 plus, well, we've got 0a2. And then we would have 3a3 equal to z. So all I'm going to try to do is just simply solve for a1, a2, and a3 in terms of x, y, and z. The way I'm going to do it is just a little bit of substitution, I think. So let's see. If we look at our first two equations, we've got 1a1 plus 1a3, that equals x. We have 1a1 plus 3a3, that equals z. Well, if we solve for the first one for a1, that says, well, a1 would equal x minus a sub 3. And now I'm going to plug that into my other equation that I kind of peeled off here. So it says we have x minus a sub 3. Again, I'm just plugging that in for a1 here. Okay. But then we still have plus 3 times a sub 3 equals z. Well, that tells us, hey, that's going to be x plus 2 times a sub 3 equals z. And again, I'm trying to solve for my constants a1, a2, a3. Well, here we can solve for a sub 3. We can just say, well, we can subtract the x over, so z minus x. And then we could divide by 2, or equivalently multiply that by 1/2. And that'll give us our value for a sub 3. Okay, so that's one thing that's going to be useful. Well, now I'm just going to simply plug that back into our other equation. So we said, hey, a1 is going to be x minus a sub 3. Well, let's plug that in. We've got 1/2 times z minus x. And again, I'm just going to solve for a1 here. I've already got it solved. I'm just going to simplify. So we've got x minus 1/2 times z. I guess we would have what? Plus, so plus 1/2 x. And now I'm just going to combine my like terms. So 1x plus 1/2 x is going to be 3/2 x minus 1/2 z. So now I've got a1 in terms of my components, x, y, and z. We don't need the y, obviously, in this case, just x and z. And last but not least, let's see, I think the only equation we haven't really played with yet is our second equation from before. Right? We haven't done anything with this one yet. We've got a1 solved for. We've got a3 solved for. We just need to solve for a sub 2 now. So it says a sub 1. Let's plug that in. Well, we know that that's 3 over 2 x minus 1 over 2 z. It says then we have plus a sub 2. That's the one we don't know. And then 2 times a sub 3. And again, a sub 3 we said is 1/2 times z minus x. So let's see, 2 times 1/2 times z minus x. And we said all of that is going to be equal to y. So let's set it equal to y. And again, now it's just the same thing as before. We're going to combine like terms and then solve for a sub 2. Well, let's see, the 2 and the half would cancel, I guess. We have 3 halves x. It looks like we would have minus an x, so that would leave us with 1/2 x. It looks like we have negative 1/2 z plus 1z, so it looks like a positive 1/2 z to me. We still have our plus a sub 2 hanging out, and then that's equal to y. And again, now we can just simply solve for a sub 2. It says a sub 2 would be, if we subtract negative 1/2 x plus y minus 1/2 z. And again, now we have, we've solved for a sub 2 as well. So the idea is, again, by doing this, we've got values. It says if you want to, write any vector x, y, and z, pick your favorite numbers, x, y, and z. And now we've got a formula that will determine what a1 should equal, what a2 should equal, and what a3 should equal. We know a formulas to figure out these real number coefficients so that after we do the arithmetic, we'll get our desired vector. And again, these are what the coefficients would have to equal, in terms of x, y, and z, in terms of x, y, and z, and we've also got a sub 3 in terms of x, y, and z. Again, obviously 2 of them don't use y, but that's all there is to it. So now we've shown that our vectors are linearly independent. They also form a spanning set, and therefore these 3 vectors also form a basis for R sub 3. So the moral of the story is you don't just have to use the unit vectors for a basis. You can certainly use other vectors as well.